Hello and welcome to the next webinar in our series on EELS and F10 data acquisition and analysis. Our speaker today will be Dr. Liam Spillane. Today, Dr. Spillane, excuse me. So Liam hails from Imperial College London. Liam has been a true renaissance man for Gatan, having many roles within the company, from installation and training to software development to application scientist. So he's really seen it all. Before we start, just a little bit of housekeeping. So questions can be entered in the question panel. We will get to connectivity questions straight away, but anything related to the content, we're going to hold until the end and try to answer all the questions together. So without any further ado, I'll hand everything off to Dr. Spillane. Take it away, Liam.
Great, thanks, Ray. Okay, so good morning, good afternoon, good evening to everyone, wherever you may be in the world. So I'm going to be talking today about advantages of direct detection for EELS data acquisition. So overview of the talk, it's kind of broadly split into two sections. So we'll start off with electron detection in TEM. So a few fundamentals, moving on to indirect detection versus direct detection. And then we'll end with some application examples. So we'll start off with just a couple of imaging and diffraction examples. Then moving on to counting EELS, high-speed mapping, and finally some low-loss analysis. So details of a post-column spectrometer. So the final projector crossover of the TEM acts as the source object for the spectrometer. So the core part of the spectrometer is a 90-degree prism. So electrons enter the 90-degree prism and are dispersed in energy loss. So this is how we form the energy loss spectrum. So we have tuning multipoles that are used to focus the spectrum in the plane of the energy selecting slit. And then after the slit, we have projector multipoles. And the projector multipoles are used to change the energy dispersion or the spectrum magnification and also transfer the spectrum to the electron detector. So there's a few kind of challenges when we want to detect the EELS spectrum. So first of all, we have features present from really, really low energy, so milli-eV, so like phonons, plasmons, right up to keV energy, so kind of high energy core loss. So we've got a really big energy range that we need to capture. We also have a really large range of feature intensities, so we need a very large dynamic range to capture all of the spectrum. So this example here is a copper 2 oxide spectrum. So the ZLP max intensity here is 2 × 10⁹ counts, and the silicon K intensity is only around 1,000 counts. So even in this spectrum, which isn't over a really big energy range, it's less than 2 keV, we still have a 6 order of magnitude change in intensity. So what would be the features of an ideal detector for TEM? Essentially, we want something that responds to every electron, so it has high quantum efficiency. Something that responds, or basically knows the position of the electrons, so high spatial resolution. And something that doesn't give a response where we don't have electrons, so we want something that's low noise. We might want to know when the electron was detected, so that would be temporal resolution. We might want to know how many electrons have arrived, so we need a high dynamic range. We want a linear response. Also, we might want to do things that are more exotic, so the energy of the electron, as momentum of every electron, and spin of electrons, and so on. In general, we're mostly actually interested in these top three, so quantum efficiency, spatial resolution, and low noise. And these are all wrapped up in this property that we call DQE, or detector quantum efficiency, which is a function of spatial frequency. So that's just a measure of kind of the detector performance. We'll kind of cover that in a little bit more depth in a few slides. So we have really kind of two kind of main kind of types of technology of electron detectors in TEM. So we have a traditional indirect detection camera. So we have a fiber-coupled CCD or a fiber-coupled CMOS sensor. So kind of in the indirect detector design, you have a scintillator, which converts electrons to light, a fiber optic that's bonded to the scintillator, which channels that light through to a CCD or CMOS sensor, which is at the bottom of the stack, and the sensor does light to charge conversion. So you have a fast electron incident on the scintillator, generates photons. Photons pass through the fiber optic and then kind of interact with the CCD or the CMOS sensor. So that's how we kind of deal with our information transfer. So there's a few disadvantages with this approach. So we have a lot of scatter in the scintillator material. We have backscatter in the fiber optic. We have scattering of light in the fiber optic. And we have kind of distortions from the fiber optic itself. So what essentially happens is you have kind of information that kind of is a point of interaction on the sensor surface, ends up being kind of spread all over this kind of volume in the detector, and that's a property that we call point spread. So kind of spreading information that would otherwise be at a single point, and it's something that we want to try and avoid. So for the direct detection camera, we just have kind of active pixels that are thin, and they're kind of supported by support material, and we're kind of directly measuring the electron beam with the sensor itself. So a fast electron will pass through a sensor pixel, generate electron hole pairs, and we kind of have this direct method of measuring the charge of the sensor. So we have some limitations here. We have scatter in the sensor itself again. So we have a low Z sensor here instead of high Z scintillator. We can get pixel damage. But one of the big advantages here, if you kind of compare these two guys, is you can see that we don't have anywhere near as much kind of scatter in the sensor, but mostly because it's so thin compared to the indirect detector. So the direct detection camera inherently has a low point spread function compared to the indirect detector, which is a good thing. So kind of that gives us a resolution benefit. Okay, so we've covered point spread. So what about DQE? So I kind of briefly mentioned DQE earlier. So the DQE is essentially kind of a measure of signal to noise ratio out and signal to noise ratio in. If we have a perfect detector, we're going to have a DQE of 1. So we have this other concept called Nyquist frequency. Nyquist frequency defines the maximum spatial frequency that can be measured by a detector. So the minimum resolution or maximum spatial frequency is going to be given by twice the pixel size. So DQE is a function of sampling frequency or kind of the resolution that we're looking at. So when we're looking at detector performances, we're really generally using these curves of DQE versus sampling frequency. So that's what we're going to look at now. And then we have this Nyquist limit of a physical Nyquist limit of 1. So we'll start off with film and indirect detection. So this is kind of a nice segue into like, what's the point of direct detection? So if you look at the DQE curve of indirect detection compared to film, it's actually kind of, you know, they're easily kind of equivalent at very low spatial frequency. But then as you kind of increase the spatial frequency, so at higher resolutions, film, they outperforms an indirect detector by quite a lot. So that's really the rationale behind kind of making a direct detector. We want to have some sort of electronic detector that outperforms film. So the first kind of piece of the puzzle, we have the direct detector DQE curve. So you can see that this is just the direct detector as is in linear mode, and we're getting this improvement in DQE just by having this low point spread function detector. So that kind of low point spread, super thin transmission sensor gives us a DQE curve that beats film. So we're already winning. But then we have this kind of other method, electron counting. So what does electron counting do? So counting has a huge improvement in the DQE curve. So we kind of we almost double, or we more than double the DQE performance at kind of low to mid spatial frequencies, and we're outperforming the direct detector and the film, even right up to our Nyquist limit. Again, we have this other kind of concept called super resolution, which we'll touch on in the next slide. Super resolution does something kind of neat. We actually end up with more pixels in the image than on the sensor. which is great for field of view, but kind of one of the big advantages is that we kind of boost our DQE at low spatial frequency, and then we also boost we boost the DQE with respect to just kind of regular counting right up to the Nyquist limit. Okay, so this is all maybe seems a little abstract. Basically, higher DQE is better. That's what we want. So, okay, so what is electron counting, and why does electron counting improve the detector signal to noise ratio? So electron counting and super resolution. So this is just kind of a schematic or a graphical representation of our sensor. So we have electrons or an electron. An electron enters the detector and generates some signal because it scatters in pixels. So we have charge that's kind of spread over a number of pixels, so kind of 4. And the charge is collected in each pixel. So counting reduces the highest charge down to 1 pixel. So we're kind of separating these individual electron kind of interaction events down to just kind of zeros or ones. So we either have a count or we don't. But you can kind of do something clever with this, because the center of mass of this interaction is kind of, we have basically this interaction is spread over multiple pixels. So we can kind of do this centroid method where we find the kind of center of the mass, center of mass of the interaction. And you can basically subdivide these physical pixels into a subgrid of 4 pixels. So this is super resolution. So super resolution gives us our event localized to sub-pixel accuracy. So the benefit that we already saw in the previous slide, we get improved DQE at low and high frequency. And we also get these kind of super resolution images that are bigger than the physical sensor size of the camera. So our 4K detector gives us an 8K image. So the advantage here is that you end up with kind of a higher, you basically boost your field of view if you're using super resolution, and you get improved DQE. So it's pretty useful. Okay, so what does electron counting do in practice? So we have to run fast to do the electron counting. So the K2 runs at 400 FPS in counting mode. K3 runs at 1500 FPS in counting mode. And the whole point of that is that we can kind of separate these individual electron events and register them digitally. So this is an example of a frame from the K2. So it's a single 2.5 millisecond frame using conventional charge readout. And then we look at the same frame after counting. So if we compare these two, kind of the main differences here, if you first of all look at kind of the electron strikes, the scattering events, you've got all of these kind of like white spots are like electron kind of scattering. So they're different sizes and they're different intensities. If you look at the counting frame, you've just got lots of single pixel events, and the intensity is uniform. Then if you look at the black regions, so we have noise in the background here, so it's not uniform black or 0 compared to the counting frame. You've got 0 intensity everywhere. So counting removes the variability from the scattering, and it rejects the electronic read noise. And this is how we get this really high DQE. So we restore the DQE by electron counting, which is a really big advantage in imaging performance. So we have 2 detectors manufactured by Gatan. So K2 released in 2011. So it's approximately 4K camera, 400 FPS in counting mode, 400 spectra per second in EELS mode. K3, the newer flavor of counting detector. So 3.5K, 3.5K sensor, 1500 FPS in counting mode, 3000 EELS spectra per second in EELS mode, and it can do, there's an in-situ kind of counting option for K3. So the primary difference between the two cameras is the speed. So the K3 runs quite a bit faster than the K2. We also have some improvement in DQE. So the solid line here is the DQE curve of the K3 in what we call CDS mode. So you see it's kind of higher than what we saw for K2. Okay, but what does this all mean in practice? So what does it This is all nice kind of specs and technical information, but what does it mean for our data? So we'll kind of move on to the application examples. So we'll start off with imaging and diffraction. So the first thing we'll look at is some imaging examples of this metal organic framework samples. So these samples are really beam sensitive. So this is an example of trying to look at this specimen with a fiber optic coupled CCD. So regular imaging conditions with this beam sensitive sample, and it looks like everything is amorphous. So you can't really see any crystalline structure in these particles at all. If you do the same imaging in low dose conditions, so we're looking at just 4 electrons per angstrom squared here, then the story is quite different. So by using this low dose kind of high sensitivity detector, you're able to retain the crystal structure because we're not completely destroying the sample. And then because we do that, we're able to resolve interface structures, and we kind of can see surface layers and defects in the sample, which was impossible with the indirect detector. So this work was published in Nature Materials. So if anyone's interested, take a look at the paper. Another example, Magnetite nanoparticle orientation mapping. This is quite cool. So we have these Fe3O4 nanoparticles, and from a single low dose TEM image, so this was done with K3 IS, we're able to do this cool in situ mapping. So it was done at 300 kV, so the dose is higher than in the previous example, but it's still what we would consider pretty low dose, so only 14.6, like kind of around 15 electrons per angstrom squared. So what's been done here is we have this kind of just this single image, but we have sufficient signal to noise ratio and resolution in this single image to pull out the orientations of different nanoparticles. So we've kind of have subregions that we've kind of sampled here, or have been sampled by these guys at Los Alamos. So we've done Fourier transforms from these subregions, and then been able to kind of have this cool orientation map that you see, which is figure C. Okay, so that's imaging, some nice image examples. So we can see that we were already having some benefits for imaging and diffraction, but as this is an EELS presentation, what about EELS? So the detector noise model in counting mode, we have kind of 4 main factors. So we have shot noise, photon conversion noise, readout noise, and gain noise. So what we're doing when we're electron counting is we're essentially throwing away 3 of those. So all the instrumentational sources of the noise are removed by counting the electrons, and the only source noise left is pure shot noise, which is strictly dependent on the total amount of signal. So that's going to be good for EELS. Okay, so what about the point spread function? We already touched upon point spread in imaging, so having a lower point spread was better for our DQE curve, gave us better resolution. What's this going to do for EELS? So for indirect detectors, the energy resolution typically degrades with energy dispersion. So often we really need to make a compromise between either we run at high energy range, so low dispersion, and low energy resolution as a result, or if we want high energy resolution, we need to work at a smaller energy range, so higher energy dispersion. So, you know, we either need to work at one end of the extreme or try and find some compromise in the middle. But due to the low point spread of this kind of transmission counting detector, this doesn't apply for our counting detector. So here's an example of 2 zero loss peaks. One from a direct detector, so K2, and the other from an indirect detector, so CCD camera. So this was done on the same microscope, low dispersions, the lowest dispersions for the system. So you can see that even at low dispersion, the direct detector full width half maximum is still very sharp. So we have around 0.9 EV full width half maximum for the K2 ZLP, whereas the CCD ZLP, the full width half maximum is way worse. So we're kind of approaching 5 eV maybe. Yeah, so we basically can maintain energy resolution whilst keeping field of view. So we don't need to make this compromise. So that's super useful. So let's move on to the application examples for EELS. So we start off with counting EELS. So the first thing that we will look at, first sample that we're going to look at is strontium titanate and some core loss analysis. So we have two target ionization edges here. So we have the titanium L at 456 eV, strontium L at 1940 eV. So they're quite far apart in energy. So the examples that we're showing here, the spectra are required under the same experimental conditions, same sample ROI, and a similar energy field of view of the 2K, around 2K eV. So if we kind of look at the spectra, it's very clear, there's very clear differences here. So if we start off with the titanium, you can see that in the counting data, so the blue data, all four of our titanium L multiplet peaks are very clearly resolved in our spectrum. So, you know, what I've said is true. We have improved energy resolution due to the low point spread. So that's really useful. But because we're doing this at a low dispersion, we also have large energy range at the same time. So we can capture the strontium L23 edge in the same spectrum. Then if we look at the strontium edge, basically, you know, compare this one with this one. So our counting detector has much better noise performance. So the noise floor is lower, the quality is better. And then kind of one thing that's quite apparent here is you can resolve the L2 line of the strontium L edge in the counting data, but you can't resolve that peak in the, you know, the data from the CCD. So yeah, reduced noise allows the less intense strontium L23 edge to be captured with better signal to noise ratio. Yeah, so better energy resolution, better chemical analysis, better noise performance, so kind of better data quality. Okay, so we'll look at the same sample in a different way. So here, the microscope and the spectrometer have been set up to deliver the same energy resolution on both detectors. So set up for 0.9 eV. And this was done fairly low beam current, so 18 picoamps. So straight away, if we look at the difference between the two spectra, so the solid teal is the direct detector, the red is the indirect. So you can see that the energy range that we have to have for the same energy resolution on the kind of the indirect detector is much smaller. So we have to have a higher dispersion to get the same energy resolution, which is already hurting us because you can see an ionization edge here, so probably carbon, that we don't see in the red spectrum. If we then actually look at the data a little more closely, you can see that even though we have, you know, basically we have very little noise with the counting detector in spite of using a pretty low probe current. So, you know, if we look at the titanium first, you know, we can say, okay, we can see all four peaks in both spectra, but the kind of the differences is more striking if we look at the oxygen. So if we make comparisons between the oxygen, there's fine structure that we see in the counting data. So these two kind of split pre-peak on the oxygen K edge that we don't see at all in the indirect detector data, the CCD data. So we can do accurate chemical analysis even at low dose with a counting detector, which is really powerful. Okay, so moving on. So atomic resolution mapping. So this is lanthanum barium iron oxide, single crystal, probably multi-layer. So this was done with Titan G2, like probe corrected. So this was done at 300 kV. So fairly big energy range, so 400 eV up to 2300 eV. Total exposure time of 80 seconds. And then kind of moderate pixel times of 10 milliseconds. So, and then energy resolution 1 eV. So here we're going to make some comparisons between the EELS data from the direct detector and the indirect detector. Whoops, pressed the wrong button. So, okay, so gain artifacts. Gain artifacts create fixed pattern noise in spectra from the indirect detector, which limits the interpretability of the spectra. So if we look at the difference between the red, which is the indirect data, and the blue, which is the counting data, you can see that we have this really nice, smooth kind of background on the counting data, and then again here. But the red is much more kind of, has these kind of chunky or kind of jaggedy artifacts. So where we have kind of strong features, that doesn't really hurt us that much for the data. You can see that there's oxygen, iron, barium, lanthanum. But if we have something that's a very, very small feature, then kind of it becomes a little difficult to pull kind of the information out of the spectrum. So the example here is that we actually have fluorine in this sample, and you can confidently say that you have fluorine if you look at the counting data, because you have this very smooth background and then kind of this post edge kind of smooth region. So we obviously have a feature here in between 680 and 700 eV, which is a trace kind of signature of fluorine. We can't really say that with any confidence in the indirect detector data. So by doing direct detection, kind of counting EELS, we've improved the detectability here of the fluorine. We've also got improved chemical analysis. So if we look at the oxygen K edge, you can see kind of 3 distinct peaks in the pre-edge here. So we've got this peak, this peak, this peak, which in the indirect detector data, you can't really kind of see that fine structure with the same degree of precision. So improved detectability, improved chemical analysis. Finally, if we go and do the elemental mapping. So this is really cool. We get some really nice atomic resolved maps in spite of using a pretty high beam energy. So 300 kV is not necessarily optimal for atomic EELS, and kind of a short moderate exposure time of 10 milliseconds. Okay, so in terms of beam sensitivity, we've just looked at 2 things that are quite easy, the fairly beam resilient oxides. So what about something that's a bit more challenging? So this is a great example from a polymer blend. So this is a kind of a blend of polymers that's for a solar cell. So this is a highly beam sensitive sample. We're interested here in phase separation and domain sizes. It's really hard to get contrast in TEM. So we're trying to do STEM EELS spectrum imaging. So we have these 2 phases, this guy on the left and this guy on the right. And then kind of what differentiates these 2 phases is you have some fluorine in the one on the right, you have some nitrogen in the one on the left, but really you have hardly any nitrogen in this guy and you have hardly any fluorine in this guy compared to all of the other elements. Basically, it's going to be mostly carbon with some trace nitrogen or some trace fluorine. So the aim is to perform trace elemental mapping of these elements that are unique to each phase, so nitrogen and fluorine. Okay, so again, a comparison between the 2 spectral data sets. So first of all, if we kind of look at indirect versus direct detector, this is actually kind of a side kind of interest. So because of the low point spread, we have much better resolved pi star peak on the carbon K edge. So we'll zoom in a bit. Yeah, so you've increased sharpness of the pi star peak. But what's kind of more important for our result here is that we're able to pull out this trace nitrogen. So we have this tiny little nitrogen peak, but because our counting kind of background is super smooth, we have this really high quality spectrum, we're able to see that above background. Whereas again, as in the previous example, you can't do the same thing with the indirect detector. So yeah, kind of so in summary, here's the maps. So we were able to do successful phase mapping in this beam sensitive polymer sample by using counting EELS. So right down at the bottom, we have this kind of color mix, and you can pull out the phase information, which is super cool. So what next? high-speed mapping. So this is a K3 example. So just as a recap, K3, the main differences are the speed. So 1500 FPS in counting mode, and then 3000 EELS spectra per second. So what does that mean for our data? So in terms of dynamic range, it helps us. So this is how a EELS spectrum would be projected onto the CCD camera. So we have a spectrum that's 260 rows high and 2048 channels kind of in the dispersive direction. So it's kind of fairly small in height with respect to the full height of the CCD. So the full height of the CCD is 2048 channels. So we have a much kind of the smaller spectrum in the non-dispersive axis. So what are we doing with the K3? We actually increase that spectrum height out to 2048 rows. So we have a much, much taller spectrum. And then in the dispersive direction, we have 3,456 energy channels. So what's the point in that? So first of all, it helps us because we're spreading the zero loss peak over a lot more channels or pixels. So as I touched on earlier, because we're doing this electron counting, you have to go fast. And kind of the reason that we go fast is we have this sort of threshold dose or dose rate at which the counting doesn't work due to coincidence losses. So for acceptable counting on the K3, we need the dose rate to be around 80 electrons per pixel per second. So just as a comparison, for the K2, we could only go up to 20 electrons per pixel per second for K2. And the reason that we've got this kind of increased counting threshold with K3 is because we're going faster, we can have more electrons on the detector. Okay, so the EELS spectrum is 2048 pixels per energy channel, so that's the height of the spectrum. That equates to 164,000 electrons per channel per second. And then we can also do something clever with the fast shutter. So if we have higher arrival rates than we would like, so if we want to look at the zero loss peak or something that's super bright, we can actually modulate the spectrum with the fast shutter. And the electrostatic shutter can run at speeds of 100 nanoseconds. So it's super fast. So all this kind of numbers kind of come together and allow us to have around 550 million electrons per channel per second, which equates to around 90 picoamps per channel. So we can actually put a fair amount of current in a single channel on the detector. So that's the dynamic range. Okay, so why is that useful? So here's an example of ultra-fast electron counting and kind of some chemical and compositional analysis. And we're comparing conditions on K2 with conditions on K3. So yeah, okay, so this is 200 kV. We're looking at big energy range, so 250 eV up to 3,250 eV, and a pretty high probe currents at 200 picoamps, pixel size around 0.3 nanometers. So this is what we'd have kind of running at full speed with the K2. So we're able to map chromium, ruthenium, titanium. Well, yeah, so this is what we're mapping. This is our field of view at 2.5 milliseconds at K2 speed. So if we kind of go full speed on the K3, so 0.3 milliseconds, this is what we have. So we have a much, much bigger field of view. And because with the K3, we have this big energy range of 3000 eV, we're able to actually collect loads of signals. So we've got lowish energy edges like chromium L in this kind of data set, 575 eV, silicon L right down at 100, and then we're going out to ruthenium, so 2800-ish eV. So K3 versus K2 speed. So for the same conditions and the same spatial resolution, we've got an approximately 10 times higher spectral array, so we can map a much larger field of view in the same time. So there's actually kind of specimen regions here that we don't even see here. So there's this copper layer that we see kind of in this kind of larger FOV kind of data set that we could potentially have missed in the other data set. Yeah, so increased energy range and dynamic range. so we get more ionization edges in a single spectrum. Okay, so if we actually pull out energy loss spectra from the data and have a look at them, so we've got our titanium L edge, oxygen K, chromium, ruthenium, copper L. So as you can see, it's still possible to do chemical and compositional analysis even at the high speed. So we have sufficient quality in our data to kind of pull out fine structure in some of the ionization edges. So we can see the titanium LNES, chromium LNES pretty well. We can also tell pretty easily just by looking at the copper that it's 2+ character. So yeah. Okay, so final example. We're going to look at low loss spectrum imaging. So this is something that's kind of new. So one thing, another thing that's different between the K3 EELS and the K2 EELS is that we can do dual EELS now with the K3 where we couldn't do that with K2. So this gives us extended dynamic range, extended energy range. So we have two spectra. One is low loss, one is labeled high loss. But we're kind of free to kind of separate those in energy by up to 2000 eV using the drift tube. So you could use that to give you a very big kind of separation, which would give you up to 5000 eV energy range, or you could overlap the spectra a lot to give you increased dynamic range. So how does DualEELS work in practice? We have basically a very fast sequence of events. So we do a fast exposure, which gives us our low loss. So in this case, it's a low loss spectrum. You can see the ZLP here, probably plasmon there. Blank using the fast shutter. Read, so that's the low loss spectrum. Apply the energy shift. And then we grab our long exposure. So this is our high loss. And then we read. So we very fast sequence of grab this one, grab this one, grab this one, grab this one. So energy shift, yeah, re-expose, fast exposure, get the low loss. So that's DualEELS. So something that's really cool that you can do with this with the K3 detector. So we've already increased our dynamic range with respect to K2, but if we do DualEELS, we expand our kind of dynamic range even further. So this is an example from a semiconductor multilayer sample. So we have silicon layer, silicon oxide, I think titanium nitride, and then we have this hafnium, so hafnium oxide layer. So what we've done here is we've done, this was done at Berkeley. So thanks to Berkeley and Ensign for allowing us to use the equipment. So this was done on the Team 1 microscope. So 300 kV. So this is a pretty high probe current, so 120 picoamps using an XFEG. So it's a monochromated Titan. We were monochromated. It's kind of the older design monochromator. So we're not looking at kind of ultra high energy resolution. We've got an energy resolution of around 90 millieV here, and then we're using a 30 millieV channel dispersion. So it took around 4 minutes to have this 256 by 212 size data set. And then we have DualEELS. So we have kind of our low loss and our high loss spectrum image. So we were able to do this lower exposure where we have 0.3 millisecond spectra here using the far shutter to kind of attenuate the beam. So you can see we have our zero loss peak. And then what we do is we have our energy offset here for the higher loss set so that we have the ZLP maximum outside of the field of view, so not on the detector. And that allows us to open up the fast shutter and have our exposure time way, way higher. So we're looking at kind of 5 milliseconds in the low loss, 0.3 milliseconds in the zero loss. And then because we have the ZLP tail just in the data here, it's really easy to then just splice the two spectrum images together. So you could splice the individual spectra, or you could splice the two spectrum images, and then you end up with this like really high, much improved dynamic range data set where you have the zero loss peak and all the low loss data out to kind of almost 100 EV in this case at a decent signal to noise ratio. So, really good quality spectrum, zero loss peak, and low loss, so you can kind of pull out quite a lot of useful information about the Hafnia here. So probably the band gap, a bunch of other stuff from our kind of plasmon and kind of other low loss region. So this is something that we weren't able to do before with K2, and it's kind of exciting and kind of fun to try this new stuff with K3 and DualEELS. So that's the final example. So in summary, direct detection EELS. So using a transmission electron counting detector gives you high energy resolution at low energy dispersion due to the low point spread function. So this is really good for chemical analysis, gives us big energy range, helps us look at fine structure, kind of, all the things that we want to do in EELS. Also, by working at a low dispersion, we're actually putting more signal into each energy channel, which kind of helps us further. So that actually kind of helps with your signal to noise ratio, makes you can use faster exposure times, etc., etc. Also, by removing instrumental noise, direct detection EELS gives you high quality, low noise electron energy loss spectra. So those two work really kind of well in parallel. So because we have point spread, low point spread, we can put more signal onto the detector, which has low noise anyway. So kind of we're kind of double winning here. So this is great for trace analysis, beam sensitive materials, low dose, ultra high energy loss, basically anything with a low signal. Yeah. So K3 EELS. So we have a big speed improvement. So around 10 times and around 4 times dynamic range with respect to previous generation detector, so K2. So that's great for high speed mapping while maintaining high quality for chemical analysis. And we can do that with DualEELS. So DualEELS is great because it gives us the extended energy range, kind of up to 5000 eV if we want to use the maximum energy range. Or we can do something like the previous example where we overlap the spectra a lot, so we can get extended dynamic range, which is really, really great for low loss analysis. So that's it. So if anybody has any questions, feel free to submit to the questions pane.
Great, thanks a lot, Liam. That was a motivating talk. We did have quite a few questions coming in during the presentation, so maybe we can highlight a few of those. Also, just as a preview, I want to remind everybody that the M&M meeting, microscopy and microanalysis meeting, is still happening next week. It's going to be an all virtual meeting, and the various organizations scrambled, put this together. And if it goes as smoothly as the Canadian microscopy meeting, it's going to be a really good show. So these virtual meetings actually are quite well organized and set up. So I want to thank all the organizers who made that big sudden shift to work with everybody. Yeah, so we actually are doing demos. So there'll be remote demos from our applications lab. So there's a sign up page where we can set you up with demos of the continuum, and on the K3 counting EELS and Monarch and EDS together. The presentations are shown here that are directly related to Gatan, but there's a nice website on M&M where they show all the times and all the presentations. Yeah, and these are all in Central Time for the because the original meeting was going to take place in Milwaukee, which I was really looking forward to. Yeah, so one quick question is one of our participants pointed out that the strontium titanate data that we showed was background subtracted, and it's kind of important to make that distinction between edges with background and edges without background. So thanks for pointing that out. So there was a question about DualEELS. So you showed the DualEELS application. You said that you read the low loss and then the core loss, but how much time is there between those two acquisitions?
Off the top of my head, it's like a few microseconds. Oh, it's kind of sub-microsecond, isn't it? Something like that.
Yeah, I think at 10 microseconds.
Yeah. Oh, yeah. That's correct.
But yeah, it's hardware synchronized so that the two happen, one right after the other, so that the readout of the camera is locked together with all the shutters and the shifts, so that all happens in complete synchronicity. Also, I think you showed almost all 200 kV data. Maybe there was, but what energy range can we support on this detector?
We can support upwards from 80 kV, so 80 kV through 300 kV. So 80, 200, and 300 is the kind of the typical options.
Okay. What if you wanted to go lower than that on this detector? I guess, or for a continuum system.
So for lower kV, we have you can have two detectors on the system. So you can have the indirect detector, so the phosphor coupled CMOS, which is good for low kV, and the K3 is good for the high kV. So a two camera system is kind of optimal if you want to do both kind of low kV and high kV work. So you would do kind of your high energy work on the direct detector and then the low energy on the indirect detector.
Okay, great. Yeah, I guess the indirect detectors at low kV really don't suffer from point spread like they do at the high kVs.
Yeah, correct.
Yeah. So also, one panelist one of our participants was asking about looking at momentum resolved EELS, so omega Q EELS. Is that something that we can support on this? So the short answer is yes, but can you elaborate on that, Liam?
Yeah, it is something that we can support. And it's actually not too different from the regular the K3 alignment. So the omega Q setup on the standard camera is we kind of changed the optics of the system so that the spectrum height is it's made a lot, basically more pixels. Our spectrum is taller, but we don't have to make so many changes with the K3 detector because we're already in an alignment regime where we have this really high spectrum anyway. So kind of electron optically, it's pretty much the same or similar to the standard K3 alignment. We just would use the omega Q slit and kind of a different software option for the acquisition that would kind of give you kind of a non-dispersive axis, which is in kind of an angular unit instead of kind of a non-calibrated unit. So yeah, it's pretty cool. And then that's also going to be beneficial with the counting detector because omega Q is kind of, you can have a fairly weak signal, so the benefits that you'd get from having the super low noise kind of the counting detector would be quite exciting, I think, to use in a omega Q regime.
Yeah, maybe we should do a webinar focused just on that. That would be really interesting.
Yeah.
Let's see, sure. I think we have actually time for one more question, and just came in, was asking about sensor damage. There was in the initial slide when you're talking about direct detection, you said, well, the one drawback of direct detectors is that they can damage. And the question was the comparable lifetimes of direct and indirect sensors. Can you comment a little bit on that, or I could take that question?
Yeah, I think maybe you could say in terms of absolute hours, but I don't believe we've actually had to exchange, so the sensor's actually a field exchangeable part, so they can be changed out, but I don't believe we've ever had to change one due to radiation damage. If you kind of park the beam on the sensor and you went off for a coffee or something, then you might be in trouble. But there's a bunch of kind of fail-set. So there is kind of a dynamic kind of sensor protect. There's basically some kind of active measure of dose on the sensor. So if it hits this kind of threshold, which is deemed to be too high, the camera will automatically retract. So you kind of have to try pretty hard to damage the. I mean, they are more sensitive than the indirect detector, but it's more radiation hard than you probably think. I mean, you can use it as a regular imaging camera. You can use it for, particularly with the continuum where we have the fast shutter, you can use the detector for diffraction, for seabed, EELS. Obviously, EELS is like a high brightness application if you're looking at low loss. So yeah, it's more versatile than you would maybe assume. Do you know the kind of
it is
hours?
Quite robust. For the K3, actually, I'm not sure what the number is. I'll have to look that up. For the K2, I think our spec was 5 × 10⁹ electrons. But like you said, they really didn't seem to damage by that, because we actually found a mechanism. One of the damage mechanisms is trapped charge in oxides, which causes leakage. And it turns out if we anneal the sensor, and there's a regular process of annealing the sensor, that will remove that trapped oxide and actually bring you almost back to a fully fresh sensor. So it's it is quite robust. But as you mentioned, yeah, if you do park the beam on it and for some reason the safeguards failed, you could damage the sensor. But the same is true for a phosphor scintillator. I've seen some pretty badly melted phosphor scintillators where someone parked a diffraction spot on the sensor.
It's actually more work to change the indirect detector than it is the direct detector, isn't it?
Okay, yeah. So all right, we're getting a little off topic here.
Okay.
It's a past time here. So why don't we call it there? If there's any more questions, we'll pull those out and answer them via email. Again, M&M meeting. I do encourage everyone to join. The sign-up fee is really reasonable since it's all online. Students, I think, are just a few tens of dollars. So that would be great. And I just want to thank you, Liam, for the excellent presentation.
Thanks.
Thank all of our participants for signing in nice and early. And have a wonderful rest of your day.
Yeah, thanks everyone.